Hi guys, in this video we are going to introduce the topic of Lewis structures. Okay, so first up, definition. Lewis structures, also known as electron dot structures, are simply molecular representations that allow us to visualize the bonding or connectivity between atoms in a molecule, right? And in addition to that, Lewis structures also give us an idea of where, if any, lone pairs of electrons reside. Right? So this is sort of our first step moving beyond a molecular formula which gives us, hey, these are the types of atoms present in a molecule. Now we're actually going to be able to talk about how those atoms are bonded or connected to one another. Okay. So the foundation of a Lewis structure, it all begins really with the so-called Lewis symbol. Okay, so what we're going to do is essentially draw upon what we talked about in terms of the electronic structure of atoms. And we introduced this idea of core electrons and valence electrons. And we mentioned how valence electrons are the electrons that we really care about when we're really asking the question, well, how is this atom going to interact and form molecules with other atoms? Right? So we're focusing in on the valence electrons. So what Lewis symbols do is take that chemical symbol and simply add a single dot for every one of those valence electrons. So we can see here that in the example of oxygen, the electron configuration of oxygen, 1s2, 2s2, 2p4. In yellow here, we've highlighted the 6 valence electrons. So we're simply going to write out that oxygen chemical symbol with 6 dots around the outside. And we can see I wrote out a list of the second row elements and their corresponding Lewis symbols. We will typically write in each single electron by itself first, so we get to carbon, 4 of them, one on top, bottom, left, and right. And then as we have additional electrons, we'll then go back and pair these up. Okay? And so this is our first step. We're bringing our attention to the actual number of valence electrons that are present on a given element. Okay, so that's going to be a sort of our foundational component of the Lewis model. But then, of course, we need to be able to represent bonding interactions within the Lewis framework. Okay? And so the Lewis model gives a very simple, straightforward way to represent a bonding interaction. In the Lewis model, we're simply going to use a line, right? So a given line here represents a pair of shared or bonding electrons. Okay. In the context of an ionic bond, remember we don't have sharing, we have an electron transfer process occurring. Well, in that case, we actually see that little electron transferred over to the receiving element. In this case, a potassium metal is transferring its electron to its only valence electron to a chlorine atom. And then the resulting configuration within the Lewis model now shows a total of 8 electrons around that chlorine atom, and we're going to enclose that in brackets and put a superscript to denote the charge. So this right here is a Lewis model of an ionic compound, right? And so note that convention of using a brackets to surround charged elements and put that superscript up there. And then remember this potassium, it's lost an electron. So we keep track of that by simply removing all the electrons. We don't go down to the now exposed lower shell where we just keep it as just potassium with a plus. Okay. And so ionic compounds in this Lewis model are relatively straightforward and something pretty close to what we've been dealing with before. What we're going to do here now then is really build up some tools and techniques for building up Lewis models for these covalent compounds. So the good news is we can boil down this process to essentially a 5-step method. Okay, we've got a 5-step method to build up the vast majority of Lewis dot structures. So what I'm going to do here is do a quick read through of these steps, and then we're going to go back through and we're going to look at examples of every single step along the way. So the first step in building up a Lewis model, remember, atoms are held together by electrons. The electrons serve as the glue holding together these atoms to form molecules. So your first step is to really figure out how much glue you're working with. You're going to have to add up the total number of valence electrons, right? And then, of course, if you're dealing with a compound that has a negative charge, well, that negative charge means that you have an extra electron. So for each negative charge, you'd have to add 1 electron. And of course, if you have a positively charged species, then you're going to be subtracting 1 electron for each positive charge. Okay? All right, once you've added up your total number of electrons, then the next step is going to be to really draw an outline, an initial outline of how those atoms are going to be arranged in the molecule. And the rule that you're going to use is to placing the least electronegative atom in the center. All right, so we're going to have to go back to our electronegativity chart and our electronegativity trends, which we'll recap here in a second. You have to identify that least electronegative atom and plop it right there in the center. Okay, and then also keep in mind that hydrogen atoms, because they only want 2 electrons, and 2 electrons, that's satisfied by a single bond, these hydrogen atoms are always going to show up on the outside or terminal positions. And again, we'll see examples of what I mean by that here shortly. Okay, so number 3, right, now that we've counted up the electrons, drawn out an initial outline of the structure, now we're actually going to start gluing together that outline, right? We're going to place 2 electrons between every 2 adjacent atoms to represent those chemical bonds. And we have to keep track of how many electrons we used up in this process, because we've got a total number of electrons here from the first step, and we need to do some bookkeeping along the way. Once you've paired together all of those electrons in step 3, step 4 is going to be to distribute the remaining electrons as lone pairs with the goal of giving octets. Remember, atoms like to have that full outer shell. So give those octets, or in the case of hydrogen, you'll just have a duet, to as many atoms as possible. And you're going to do this by adding lone pairs to terminal atoms first. You're going to add those lone pair electrons to the outside atoms. And you can perhaps, aid your memory in remembering this by remembering that, well, hey, we put more electronegative atoms on the outside. So the more electronegative atoms want electrons more, so give them those lone pairs first. Okay, however you want to remember that, give those lone pairs to the terminal atoms first. And then finally, if you've used up all of your electrons and you find that there are any atoms that are lacking an octet, then we're going to introduce multiple bonds, either double or triple bonds, in order to make sure that every atom in that octet, every atom in that structure has a full octet. Okay, so let's see this in practice now. So first up, when we are finding the total number of valence electrons, remember, this is exactly what we've done before when we introduced, in our previous lectures, this idea of electron configuration and counting up the total number of valence electrons for a given substance. Basically, all you have to do, look at where, in this example, we've got nitrogen, for example, look at where nitrogen lands in the periodic table and count over 1, 2, 3, 4, 5, right? Which means nitrogen's going to have 5 valence electrons. Oxygen, in the same fashion, right here, is going to have 6 valence electrons, right? So, of course, if we have 2 oxygens, then it's going to be 2 times 6, right? So we've got our nitrogen contribution, we've got our O2 contribution, right? And we are going to be left then with 17 total electrons. Okay, and so of course, if we change this and we look at the molecule NO2 minus, right, then we're going to have the 17 electrons from NO2 plus the 1 electron because of this negative charge up here. Okay, so NO2 minus would have a total of 18 electrons. Okay, moving on to our second step. We're going to be placing the least electronegative atom in the center. Okay, so for this, we're going to look at our electronegativity table. And remember, Linus Pauling's relative electronegativity scale, fluorine is the most electronegative element with a value of 4.0, and everything else is provided the numerical values relative to that fluorine, and notice that electronegativity increases as you go from left to right and increases as you go from bottom to top. So increasing towards fluorine. So if we look at our NO2 molecule, well, we see that NO, right, O is closer to fluorine, O is more electronegative. So we're going to lay out our molecule with nitrogen at the center, right, because nitrogen is the least electronegative element. Okay. And then remember, we also have this note here. Hydrogen atoms are always going to be in a terminal position. So if you're in a situation where you have two compounds that have relatively similar electronegativities, for example, hydrogen and carbon, right? Well, you have to use some other logic to nail out what that outline of the structure is going to look like. Well, in this case, hydrogen must always be on the terminal position because it only wants to make one bond. So we're going to end up with an outline of this structure that places hydrogens on the outside perimeter or terminal positions. Okay, so remember we're working with this molecule of NO2, and NO2 we already determined previously has a total of 17 valence electrons. Now in this third step, right, what we're going to be doing is placing 2 electrons between every pair of adjacent atoms. And in doing this, we will have used up 4 electrons, right? So as a result, we only have 13 electrons left, okay? And if we were going to do the same sort of thing for NO2 minus, well, then we'd be starting off with 18 electrons. And then we'd use up 4 of them again, and we'd have 14 electrons left over, right? So moving forward within our 2 minus example, we'll actually come back to NO2 in a future lecture. NO2 minus now, we're in our 4th step, we are going to distribute the remaining 14 electrons to terminal atoms first to give them lone pairs and satisfy this octet to the greatest extent possible. So now we're dealing with 14 electrons. Now let's go ahead and put in some lone pairs. We'll put those lone pairs in red. I'm going to put, remember, oxygen with the 1 bond has 2, so this makes 3, 4, 5, 6, 7, 8. We've satisfied the octet. Similarly, we'll put 6 more electrons around that oxygen over here. Now both those terminal oxygen atoms have a satisfied octet, but we've only used up 12 of our 14 electrons. So to use up the remaining 2, we're going to add a lone pair to that central nitrogen atom. Now we've used up all 14 electrons as lone pairs in red here. So we've used them all up, 0 electrons left over, and we have our Lewis dot model according to step 4. Now in our final step, what we have to do is look back and ask the question, does every atom have a full octet? In this case, hopefully you can see that in fact the nitrogen does not have a full octet. Okay, so the nitrogen atom here has only 6 electrons. Okay, only 6 electrons. It wants 8. So what are we going to do? Well, we are going to form multiple bonds, right? So in this case, nitrogen has 6 electrons. It only needs 2 more electrons, so it only needs 1 more pair of electrons being shared with it. Okay, so to see what we're going to do here, we're basically going to take that same outline, but we're going to now take that one of those pairs of electrons, we'll say, hey, maybe take this guy, that is initially localized on the oxygen, and fold him in to form a multiple bond, in this case, a double bond, right? Double bond between that oxygen and nitrogen. So remember, a double bond, what we're really talking about here is 4 electrons are being shared between the oxygen on the left and the nitrogen atom. Then the remaining lone pair electrons, now there's only 2 lone pairs on the left-hand side oxygen. We still have all 3 on the right-hand side. we can add back in, and now we arrive at our final Lewis dot structure for NO3 minus. But of course, you should remember, because we have a negative charge up here, we're going to draw brackets around the outside and put that negative charge up there as a superscript. All right, so what we've introduced here is this 5-step process for building basic Lewis dot structures. And now what I want you to do is go ahead and move on and watch some practice videos on how we can draw Lewis dot structures for different types of elements and solve some of the practice problems. And then in the next lecture, we're going to move on to some more advanced topics in Lewis dot model construction.